nature abhors a straight line, but high-speed logistics demand absolute geometry. This is the paradox of the ginger rhizome. It is a biological fortress, tough as cured wood, stringy as industrial hemp, and encased in a skin designed to repel everything from subterranean insects to heavy machinery. Deep within its cellular lattice holds a secret weapon, gingerol, the volatile oil responsible for that signature spicy burn. But here is the catch. To turn this rock-hard biological vault into a culinary powder, you must destroy it. Yet, the moment you crush the tissue, friction creates heat, and heat is the enemy. It evaporates the flavor oils instantly, turning a potent spice into tasteless yellow sawdust. So, how do you pulverize 1,000,000 pounds of fibrous, wet, irregular obstructions into a cloud of spicy dust without killing the flavor? You cannot simply grind it. You must outsmart physics. You have to scrub it with topography, slice it with centrifugal force, and finally, freeze it into glass before shattering it with a hammer made of liquid nitrogen. Welcome to the intersection of botany and ballistics. This is the high-stakes engineering behind the world's most difficult spice. The journey begins at the intake bay of this monolithic processing facility where 1,000,000 pounds of raw rhizomes are offloaded from the subterranean soil. In this state, the harvest is a nightmare for automation, a chaotic mix of organic product and geological debris where heavy clay and silica stones are clutched tightly in the root's fingers. A single silica rock, even one the size of a marble, breaches this perimeter. It becomes a kinetic missile inside the high-speed machinery downstream. A stone hitting a slicer blade at 1,500 RPM doesn't just dull the edge, it shatters the steel, sending metal shrapnel into the food supply and potentially sparking a catastrophic dust explosion. To separate the prize from the poison, the line deploys a hydraulic gravity trap governed by the unforgiving laws of specific gravity. The machine pumps thousands of gallons of water into a turbulence chamber, creating a false floor of liquid where the specific gravity of a ginger rhizome is approximately 0.9 to 1.0, essentially neutral or slightly buoyant. While the crop fights to float, the silica rock, clocking in at over 2.0, cannot cheat physics. By fine-tuning the velocity of the upward water current, engineers create a precise hydrodynamic filter, strong enough to let the ginger dance chaotically on the surface, but too weak to support the stones, which plummet through the water column into a submerged isolation chamber. Simultaneously, high-pressure spray bars execute a hydropressure decontamination, blasting away heavy clay and reducing the biological load before the product ever touches a mechanical surface. What exits the destiner is a stream of clean raw material ready for surgical modification, but the facility now faces a new problem: the impossible geometry of the root itself. Standard industrial peeling is usually a brute force affair, where round vegetables like potatoes are simply tumbled against sandpaper walls. But ginger is topographically hostile. It grows in hands, irregular clusters of knobs, protrusions, and deep, unreachable valleys that would cause a standard knife peeler to treat the protrusions like defects, slashing them off and causing a 30 to 40% yield loss just to remove a millimeter of skin. The solution requires a machine that doesn't cut, but contours, replacing the crude violence of knives with the finesse of the Vanmark Model 2920. This unit operates like a high-speed, automated car wash for roots, where the chamber is lined with 8 rotating rolls, covered in thousands of abrasive nylon bristles spinning at differential speeds. This forces the rhizomes to tumble unpredictably, ensuring that no single side is exposed to the friction for too long. The genius lies in the flexibility of the nylon, which bends upon impact to press into the deep valleys between the fingers of the root, scrubbing away the paper-thin skin in the crevices without shaving off the premium meat on the peaks. It is a friction ballet calibrated to remove exactly 1.5 millimeters of surface material. Any faster damages the cell walls. Any slower drops the throughput below the target of 20,000 pounds per hour. The dull beige roots enter the chamber and emerge seconds later as glistening neon yellow jewels, now naked, fully exposed, and vulnerable to oxidation. From this moment on, the clock is ticking to process and stabilize the product before the air turns it gray. But first, it must pass the ultimate eye exam. In a river of millions of tumbling roots, the human eye is biologically incapable of maintaining FDA-level quality control as a piece of black plastic, a shard of wood, or a patch of necrotic rot is effectively invisible at these speeds. To police the line, the facility relies on the Tomra 5B optical sorter, a machine acting as the sniper at the gates. As the peeled rhizomes slide off the belt, they enter a free-fall zone where, for a split second, they are airborne and scanned by top-mounted and bottom-mounted laser cameras operating at specific wavelengths. The sensors analyze structural density and biological fingerprints, taught to recognize the spectral signature of healthy ginger tissue while flagging anything that deviates, be it a dark spot of mold, green glass, or a dense object, as a target. The reaction time is measured in milliseconds as the machine calculates the defect's trajectory and fires a precise bullet of compressed air from a pneumatic ejector bank. Pop. The air cannon blasts the target out of the product stream with surgical violence, knocking the rejected debris into a waste chute, while the healthy roots continue their fall undisturbed. It is a kinetic filtration system executing thousands of decisions per minute to ensure the product is pure, peeled, and verified. But it is still a solid block of fiber, and to dry it, we must increase its surface area by a factor of 10,000. Slicing ginger is a mechanical nightmare because the root is reinforced with long longitudinal fibers, essentially nature's Kevlar, that fray into a ragged, mashed pulp if chopped with a guillotine blade. To achieve a clean cut that doesn't bleed out essential oils, you cannot rely on downward pressure. You need speed. The roots are fed into a slicer that operates on the principle of centrifugal annihilation, where a stainless steel impeller spins at a dizzying 1,500 RPM. As the ginger drops in, it is instantly grabbed by the rotational force and thrown against the stationary outer wall of the drum, a wall of death, lined with razor-sharp knives, set to a gap of exactly 2.5 millimeters. Because the ginger is pinned by centrifugal force, it cannot wobble or shift as it slides across the stationary blade face, shearing off a perfect coin in a high-velocity planing action that severs fibers cleanly to seal the cell walls. The result is a mesmerizing rain of yellow confetti. Millions of uniform slices, each identical in thickness to a credit card. A uniformity that is a thermodynamic requirement. If the slices vary in thickness, they will dry at different rates, burning the thin ones and leaving the thick ones wet, creating a moisture imbalance that equals rot in the drying zone. The sliced ginger is now exposed to oxygen, beginning a biological countdown where peroxidase enzymes react with the air to oxidize the flesh, threatening to turn this neon yellow into a dirty, unappetizing gray within 20 minutes. To freeze the color in time, engineers hit the pause button on biology by sending the slices through a steam injection conveyor, subjecting them to a violent blast of atmospheric steam at 194 degrees Fahrenheit for exactly 180 seconds. This blanching process is calibrated to denature the enzymes without cooking the vegetable, shocking the chemical structure to lock in that vibrant golden hue permanently. But the slices are now soaking wet, carrying 85% water weight that must be reduced to 5% without triggering case hardening, a phenomenon where high heat dries the surface into a hard cement shell that traps moisture inside the core to create a biological time bomb of mold. The solution is zonal drying, utilizing a massive dehydration tunnel that mimics the gentle, relentless progression of a desert wind. The conveyor moves the ginger through 3 distinct microclimates. Zone 1 uses high-velocity airflow to strip surface water. Zone 2 lowers velocity, but maintains heat to draw moisture from the center. And Zone 3 acts as a curing phase with a gentle breeze to equalize humidity. The airflow alternates direction, upflow and downflow, flipping the slices to ensure no soggy spots remain, taking 4 hours to transform a wet vegetable into a brittle, shelf-stable chip. Now we reach the final and most critical challenge, converting dry ginger chips into a fine 80 mesh powder without the heat of grinding destroying the flavor. In a traditional hammer mill, friction spikes temperatures above 160 degrees Fahrenheit, a death sentence for ginger that evaporates volatile oils into the exhaust vents and leaves behind dust that tastes like cardboard. To solve this, the facility turns to a modified pin mill equipped for culinary cryogenics, where technicians inject liquid nitrogen directly into the milling chamber to plummet temperatures to minus 100 degrees Fahrenheit. At this unearthly low, the ginger oil undergoes a phase change and freezes solid, while the ginger chip hits its glass transition temperature, becoming as brittle as a pane of glass. Inside the mill, 2 counter-rotating discs studded with steel pins spin at 10,000 RPM. And because the root is cryogenically frozen, the pins don't tear the fiber. They shatter it. It is like hitting an ice sculpture with a sledgehammer, exploding the ginger into microscopic fragments where the volatile oils are trapped in a solid state within the particles. They do not evaporate. They are locked in a cryogenic cage, waiting to be released only when the powder hits moisture in a sauce, a tea, or on your tongue. The powder exits the mill in a cloud of freezing fog, a triumph of thermodynamics where extreme cold preserves the fiery heat of the harvest. The frozen powder is allowed to return to room temperature in a controlled environment before passing through the final gatekeeper, the gyroscopic sifter. This vibrating screen ensures every particle meets the 80 mesh standard, fine enough to dissolve instantly in liquid, while skimming off any coarse particles or stubborn fibers that survived the cryogenic milling. In a facility of this sophistication, nothing is wasted. The coarse fibers, skins, and organic rejects are fed into an on-site biomass boiler, a furnace that burns the waste to generate the very steam used in the blanching tunnels, ensuring the root fuels its own destruction. The finished powder flows into the packaging clean room, where gravity fillers dispense the gold dust into jars with pharmaceutical precision are accurate to 1/10 of a gram. The containers are induction sealed, creating an airtight lock that protects the volatile oils for up to 2 years. What began as a chaotic, irregular harvest buried in the earth has been refined through a gauntlet of hydrodynamics, optical sorting, centrifugal slicing, and cryogenic shattering into a pure culinary element. This is not just grinding. It is the industrial transmutation of nature, mastering the physics of friction and temperature to ensure the fire born in the field is delivered intact to the kitchen.